This is part 3 of the series Circumference and Area, and we're going to start out this part by looking at sectors of a circle. Now, a sector of a circle is simply this pie-shaped piece of a circle. Whenever you cut out a pie-shaped slice, that is a sector. And that's all a sector is part of a circle enclosed between two radii and their intercepted arc. So these are two radii, and this is the intercepted arc. That's a sector. Now, looking at the sector of a circle formula, it's very, very similar to arc length. It's a proportional relationship. So let's take a look at that. Now here we have another part to whole relationship. With arc length, we had arc length was part of the circumference, and that was the whole, was the circumference. Here, the area of the sector is the part, so the area of this pie-shaped slice is part. The whole is the area of the whole circle. So part to whole, area of sector, is to the area of the circle, pi r squared, as, and just like in arc length, central angle is to 360. So this central angle sweeps out this sector, and that's part of the whole 360 degrees in a circle. So again, area of sector is a proportion, part to whole, area to area, angle to angle. Area of sector is to area of a circle, as central angle is to 360. So again, very, very similar to arc length. So let's go ahead and work some examples and see how to use this. We'll start out with a basic example here. We have a circle with a radius of 4 and a central angle of 38. We want to find the area of that sector. So, area of sector is 2. Area of the circle as central angle is to 360. So the area of sector is what we're looking for. Area of circle is pi r squared. So that's pi times the radius, 4 squared, is equal to the central angle, 38, divided by 360. Well, I just need to solve for area of the sector, so I'm going to multiply by pi 4 squared. So we're going to multiply the numerator by pi 4 squared, and these guys cancel each other out, and we multiply this side by pi 4 squared. So area of the sector is approximately equal to, put this in our calculator, and we get 5.3. All right, let's work another example. In this problem, we're given the area. Notice 225 square inches is an area measurement, so that's the area of the sector. And we're given the radius is 14 inches. We're looking for the measure of angle RST, and that's the central angle here. So area of sector is to area of the circle. That circle with a dot in it, that just means circle, is central angle is to 360. That gives us 225 over pi 14, the radius, squared, as central angle, that's what we're looking for, over 360. This is a fairly straightforward one. That's all we have to do here is multiply both sides by 360. All right, this goes away, and our central angle is approximately, remember, always put multiple terms in the denominator in parentheses, 131.5. And one more example. In this problem, looks like things got reversed on us a little bit. We want to find the area of this really big sector. Now you can do this the hard way. You can go ahead and find the area of the whole circle and then subtract off this little sector. Or you can just go ahead and calculate it directly just by taking this angle being this central angle taken away from 360. So the easiest way is just to use 320 as your central angle in the calculation, but either way it works out perfectly fine. Let's do area of sector is 2, area of circle as central angle is to 360. The reason I do this, the more you write out the proportion, the easier it's going to be for you to remember it. So I just write it out every time, and it just becomes instinctual after a while. So area of the sector is 2 pi r is 7.6 squared as central angle. Well, that's going to be 360 minus 40, which is 320, divided by 360. And then that's all we have to do is multiply both sides by pi 7.6 squared. That cancels that out. Multiply by pi 7.6 squared. And area of our sector is approximately this put in the calculator, which is 161.3. All right, well, that just about covers area of sector. Now let's take a look at areas of some other types of polygons that we've looked at in the past. The first polygon we're going to look at here is a rhombus. The area of a rhombus can be calculated using these diagonals. Now, before we get there, let's take a look at this. If I want to find the area of this entire rhombus, you know from our study of rhombi that all 4 of these triangles are going to be congruent triangles. So that means if I find the area of one of these triangles and multiply it by 2, I would have the area of the rhombus. Likewise, if I find the area of one of these smaller triangles and multiply it by 4, I would have the area of the rhombus. And so we're going to use that concept of using triangles. In this case, we're going to use this big triangle at the top and multiplying it by 2 to determine a formula for the area of a rhombus. So let's take a look at that derivation. We start out with a formula for area of a triangle, and we want to find the area of triangle BCD, this triangle up here, using the terms D2 and D1 for these 2 diagonal segments here. So it's 1/2 base times height. Well, the base of this triangle is BD, and BD is equal to diagonal 1. So 1/2 base becomes 1/2 D1, and the height of this triangle is 1/2 D2, because as you remember, rhombi are parallelograms, and the diagonals of parallelograms bisect each other. So this piece, AE and CE, are equal. So that means this height of this triangle is 1/2 the entire diagonal. So my 1/2 base times height becomes 1/2 D1, the base, times 1/2 D2, the height. So now multiplying 1/2 by 1/2, we get 1/4 D1 times D2. That's the area of triangle BCD, this top triangle. Now, if we want the area of the parallelogram, it's the area of this triangle times 2. So it's 2 times 1/4 D1 D2, and of course 2 divided by 4, 2/4 is 1/2. So the area of a rhombus is 1/2 diagonal 1 times diagonal 2. That is the formula for the area of a rhombus, 1/2 D1 D2. And now we're going to look at the area of a kite. And it may seem unlikely, but these formulas are going to turn out to be exactly the same. So let's take a look at the area of a kite. Just as in a rhombus, the kite has 2 diagonals. And in this case, we could find the area of this kite by finding the area of this upper triangle and multiplying it by 2, because as we studied kites, we learned that this upper triangle was congruent to that lower triangle. So the area of this times 2 equals the area of the entire kite. So let's go ahead and take a look at the derivation of this area formula. Just like we did with the rhombus, we'll start out with the area formula for a triangle, and we're going to look for the area of triangle PQR, 1/2 base times height. In triangle PQR, 1/2 the base is D1. 1/2 D1 is 1/2 the base, and the height is 1/2 D2. So the height here is translated to 1/2 D2. Now we take our 1/2s, multiply them together, just like we did over here, 1/4 D1 D2. That is the area of the upper triangle. We multiply that by 2, and this comes out to 1/2 D1 D2. So, as unlikely as it is, it turns out that the area of a kite is exactly the same as the area of a rhombus. The same formula, I should say. It's 1/2 diagonal 1 times diagonal 2. Let's go ahead and work out a couple of examples just to lock these ideas down. In this first example, we have a rhombus indicated by the 4 congruent sides, and we're given this segment of the diagonal is 7, this segment is 5. What that means, of course, is that since diagonals bisect each other in a rhombus, this has to be 5, this has to be 7. So now we can find the area of this rhombus. So area is 1/2 D1 D2, which is 1/2. D1 is 14, D2 is 10. So that's going to be 14 times 10 divided by 2, which gives us 70. All right, fairly basic exercise. Let's look at another example. All right, we're looking for the area of this kite. We know it's a kite because it has 2 pairs of consecutive congruent sides. And so here is D1, which is 7. D2 is 15. Doesn't really matter if this is D1 or D2. It doesn't really make any difference because it's a product. So our area is 1/2 D1, D2, 1/2 7 times 15, which is equal to 52.5. All right, that covers the area of rhombi and kites. Now, in the next session, we're going to look at the areas of regular polygons. And so that wraps up this session, and I will talk to you in the next video.